welcome back to the third keynote talk session. I hope you have enjoyed the first two interesting and informative talks so far. Also, welcome to those who just joined us now. We are just about to start our third keynote talk session with Professor Kongying Kang from Tsinghua University, China. To let you know that we have a recorded video because the speaker today was attending another parallel conference, and he was the technical committee chair for the conference as well. So I really hope that you enjoy the presentation that we watched together today. Let me just introduce him first. Professor Kongying Kang is a professor and dean of Department of Electrical Engineering at Tsinghua University, president of Tsinghua University Energy Internet Research Institute, and president of Tsinghua Sichuan Energy Internet Research Institute. Also IEEE Fellow and IET Fellow. From 2011 to 2014, he was the director of the Center for Teaching Excellence, Tsinghua University. As the recipient of the National Science Fund for Distinguished Young Scholars, Professor Kang was supported by Folk Hing Tung Foundation and enrolled in the program for New Century Excellent Talents in the university by the Ministry of Education, awarded the leading talents in scientific and technological innovation of the 10,000 Talents Plan. He has been the principal investigator for 10 grants supported by NSFC, in which 4 of them were supported to collaborate with UK, South Korea, and United States. Professor Kang serves on the editorial board of 5 international journals, including IEEE Transactions on Power Systems and Electric Power Systems, Research, and 4 Chinese journals indexed by EI. He published over 300 academic papers, including 70 IEEE transaction papers, as well as 3 monographs in Chinese and 2 books in English. In Google Scholar, his papers have been cited about 10,000 times. He obtained 25 authorized invention patents and 15 software copyrights. I would like to invite you to listen to his and watch his presentation and enjoy. Thank you very much. Let me just add to that. His presentation is on integration, high levels of variable renewable energy in power systems.
Good morning, ladies and gentlemen. It is my great honor to give this keynote speech. I sincerely appreciate the kind invitation by the Technical Committee Chair, Dr. Farhad Shahania. I understand at this particular period, it is hard to do international travels. Thanks to the internet, we can have virtual meetings like this. At the same time, in China, we are running another international conference, iSpec 2020 in Chengdu City. It is very unfortunate that both conferences are overlapping. That is why I cannot do a live talk. First, I would like to briefly introduce the Department of Electrical Engineering in Qinghua University. These pictures show several sceneries in Qinghua University, such as the sport ground, the school river, and the library. Founded in 1911, Qinghua University has developed into a comprehensive research university. At present, this university has 20 schools and 59 departments, with faculties in science, engineering, law, medicine, and so on. Of course, Qinghua University is famous for its engineering research and education. This slide gives the basic information of our department. In the top half of this slide, you can see the website and the logo of the department. And the lower left picture shows the appearance of West Main Building, which is the department hall. We teach students conscientious academics and honest behavior, which is the motto of the department. Department of EE consists of 5 institutes, namely Power System and Automation, Power Electronics and Electric Drives, Electrical Machinery and Apparatus, High Voltage and Insulation Technology, Electrical Theory and New Technology. There are 104 faculty members in this department, including 37 full professors, 56 associate professors, and 11 assistant professors. The institutes are organized by research groups. This picture shows the research groups in each institute and the leading professors in each group. There are 9 IEEE fellows and 19 IET fellows in this department. Okay, after a brief introduction to the Department of Electrical Engineering at Qinghua University, I would like to talk about integrating high levels of variable renewable energy in power systems. I will focus on the challenges and solutions for high penetration of renewable energy in China. Energy crisis and environmental issues motivate the rapid growth of renewable energy in China. In the recent 10 years, the installed capacity of renewable energy in China increased nearly 3 times. The majority of the increment is wind and solar power, with large uncertainty and intermittence. In 2020, the renewable energy penetration in China has reached 29%. The renewable energy will continue to increase in the future. The penetration will exceed 35%, 50%, and 70% in 2030, 2040, and 2050, respectively. Renewable energy has become a development trend of energy system in China. This slide further gives the 2 scenarios of renewable energy development in China. In high scenario, the local fraction of annual energy made by renewable energy is more than 95%, very close to 100%. The rapid development of renewable energy is bound to have a significant impact on the power system in China. Rapid growth of renewable energy challenges the secure operation of power system in China. Several provinces have very high wind curtailment ratios in 2017, greatly reducing the economy of renewable energy development. In fact, many challenges restrict the accommodation of renewable energy. Here is the framework of the challenges and solutions on the different renewable energy penetration. In this framework, the renewable energy penetration is divided into 3 categories: medium, high, ultra high. On the different renewable energy penetration, power systems have different challenges in time scale of stability, operation, and planning. In addition, the cost of the solutions is also different. It should be mentioned here that the solutions and challenges are not a simple one-to-one correspondence. One solution scheme can improve several factors of power system. Accordingly, one challenge may also lead to the solutions from several perspectives. The solutions are designed to solve the transit, time mismatch, and spatial mismatch problems caused by high penetration of renewable energy. In addition, some other renewable equipment performs better in flexibility or controllability. They can also contribute to renewable accommodation. In the following presentation, I will concentrate on several aspects of challenges and solutions. At the same time, different provinces have different bottlenecks of renewable energy integration. These bottlenecks are mainly concerned with transmission constraints, flexibility, and stability of power systems. For instance, West Inner Mongolia is facing the problem of minimum load constraints in heating seasons. For Jilin province, there's no enough peak-off regulation capacity. For Qinghua province, the problem is that the transmission interface constraints are very serious. One of the challenges is that the high penetration of photovoltaic is reshaping the electricity net load curve and has a significant impact on power system operation and planning. The left top figure shows the concept of the dark curve, which is widely used to describe the imbalance between peak demand and PV generation. The right lower figure displays the dark curve of Qinghua province in 2020. The significant difference of demand between the noon and night will place considerable peaking and ramping regulation stress on conventional dispatchable generators. It should be also mentioned that the dark curve could be even probabilistic because the uncertainty of PV generation, which may further increase the difficulty of power system operation. The high penetration of renewables will substantially change the power system operation. Traditionally, the annual operation of a power system can be represented by some typical operation modes and acts as the basis of the power system related analysis. The introduction of highly penetrated renewable energy will make the power system operation modes highly diversified and variable. These modes may not follow traditional empirical patterns. On the low renewable energy penetration, the power system mode is dominated by hydropower and basically consistent with the season. With the growing renewable energy penetration, the power system mode is gradually dominated by the intermittent PV and wind power. The operation mode is less correlated with seasons in renewable energy dominated power system. This slide shows the net load curve on the different penetration of renewable energy. With the increase of renewable penetration, the energy adequacy will be significantly improved. However, the peak net load does not change significantly. Thus, the capacity adequacy is still a challenge. Accommodating variable wind power poses a critical challenge for power systems that are heavily dependent on combined heat and power or CHP plants, as is the case for North China. In these regions, coal-fired CHP plants account for most of the electricity. In winter, CHP plants must operate at nearly full capacity to meet the demand for heat, and by design must produce electricity at the same time. Facing a potential oversupply of electricity occasioned by the demand for heat from these CHP plants, wind output is often abundant in this area, and precisely the time when their output could be highest, as wind conditions are most favorable in winter. This is the main reason for wind power curtailment. In China, power system is coal-fired generators dominated, while there are a large number of flexible gas-fired generators in US power systems. Compared with gas-fired generations, the coal-fired generations lack of flexibility and has worse regulation performance. The lack of flexibility cannot fully respond to the uncertainty and intermittency of renewable energy, and thus also cause wind and PV curtailment. Subsynchronous oscillation is another challenge caused by high penetration of renewable energy. The reason of this stability problem is that direct drive wind turbines, grid, and shaft of thermal generator form negative damping RLC circuit. In view of the high curtailment ratios, China has taken a series of measures to promote the accommodation of renewable energy. The mismatch between renewable resources and load center is one of the main reasons of the renewable curtailments in north and west of China. Interregional connection is an effective scheme to better accommodate the surplus renewable energy in north and west China. The state grid has been planning and building large number of ultra-high voltage transmission lines, both AC and DC. It provides a large nationwide power balancing scope for renewable energy accommodation. Power grids in different provinces can provide flexibility for each other. Power systems in China are divided into 7 regions. The renewable resources and generation mix are different in these regions. Northwest China is dominated by PV and wind. The majority of southwest China is controllable hydro power. The generation complementarity could be improved by the flexibility of northwest China grid and reduce the renewable curtailment. An operation simulation is conducted to demonstrate the benefits of interconnection. The results show that connecting the northwest China grid with the southwest China grid can significantly facilitate the accommodation of renewable energy and reduce the overall operation cost. And the optimal connecting capacity is about 90 to 100 gigawatts. In addition, China upgrades the technology to improve the flexibility of the thermal units. Although the wind installed capacity in northeast China still increases, the wind curtailment ratios are significantly reduced with more flexible thermal units. Northeast China also built peak regulation markets to facilitate renewable energy accommodation. Dynamically adjusting peak regulation requirements can better guarantee the effectiveness of economic leverage in the market operation. Integrated power system and heat system can also facilitate renewable energy accommodation. Electrical boiler and heat water tank enlarge the operation zone of CHP power plants and make the operation of power system and heat supply system more flexible. This figure shows a demonstration project in Jilin province, which has adopted the energy storage features of heat to accommodate variable wind power. With the above-mentioned measures, the renewable curtailment ratios significantly reduced after 2016. In last year, the average wind curtailment ratio has been reduced to 4%. However, some challenges still exist and need to be solved. We make some researches on stability problems and flexibility issues. How to understand the relationship between real-time balance and frequency. There is only one frequency in a power system, which all the load and generator shares. The load and generator are synchronized like a gear wheel. We can imagine the power system as a bicycle riding by a lot of people. No inertia can be an urgent issue in high renewable penetration power systems. The frequency of the low inertia system changes more drastically after a contingency. Low inertia means the ability to handle disturbance is decreased. The blackout happened in the UK in August 2019 is partly because of the low inertia caused by the wind power high penetration. We conducted a research on power system scheduling, considering the frequency stability constraints. There are significant differences when stability constraints are considered a lot. The results indicate that ignoring the stability constraints may underestimate the curtailment and obtain optimistic penetration results. The developing grid-forming converter may mitigate the stability issues caused by high renewable penetration. Energy storage is extensively recognized as a significant potential resource for renewable energy accommodation. Although small residential and commercial consumers of electrical energy can now purchase energy storage facilities, many factors such as cost, policy, and control efficiency limit the spread of the distributed energy storage, or DES. Inspired by cloud services and the sharing economy, the concept of cloud energy storage, or CES in short, is proposed to provide the same services to these consumers at a lower social cost. The structure of CES consists of three main parts: the CES users, the energy storage facilities, and the CES operator. Cloud energy storage users can use their cloud batteries just like real energy storage devices, while the CES operator will invest and operate centralized energy storage facilities to provide storage services to these users. We conducted a case study to demonstrate the benefits of CES. The data sources are based on consumers' home load and electricity price data from Ireland. In the dataset, users' behaviors differ on the same day, and the same users' behaviors differ in different days. Compare of the cloud energy storage operation and users' separate energy storage operation on a typical day, we can find that, first, the peak value of the CES charging profile is significantly less than the peak value of the aggregated DES charging profile. And second, CES is able to satisfy the requirements of distributed users with a smaller energy storage capacity by sharing the capacity among these users. This table further compares the CES profit on the different energy storage capacity and investment costs. From this case study, we have several findings. First, compared with the users using DES, CES can reduce costs and generate considerable profits under the same storage usage demands. Second, the business value of CES mainly comes from two aspects. The first one is the lower energy storage investment costs brought by energy storage capacity multiplexing. And the second one is lower operating costs brought by optimized operation. Third, investment cost of large-scale storage energy is lower than that in DES, which can increase business value of CES. Compared with variable renewable energy sources, concentrated solar power, or CSP in short, is an emerging controllable renewable generation technique that utilizes solar thermal power to generate electricity. The obvious feature is that CSP can shift the generation from daytime to the night because it has the part of heat storage. We understand that achieving high renewable energy penetrated power systems requires considerable operational flexibility to hedge the variability and uncertainty of variable renewable energy generation. The operational dispatchability of CSP would contribute to the power system transition towards high renewable penetration. This figure gives the estimated cost performance of renewable techniques in China. Although current CSP cost is still very high, the estimated cost of CSP technology will drop sharply and be close to the cost of common thermal units in the future. Our research shows that the application of CSP in power systems has a promising future. With the increasing proportion of renewable energy generation, first, the CSP installed capacity continues to increase and the cost of CSP stations continue to decrease. Second, under the lower renewable energy penetration, the high investment costs makes the CSP uneconomical. Third, at a high penetration level, the proportion of CSP is increasing rapidly and is more competitive than electricity storage. Last, at a very high penetration level, CSP mainly provides power support, which makes it less competitive than energy storage. To demonstrate the benefits of CSP, we conducted a case study in Gansu provincial power system. We compared the performance when considering CSP a lot. The left lower figure shows the power capacity portfolio of Gansu provincial power system, mainly including thermal power, wind power, PV power, and hydropower. The results of the empirical study demonstrates the benefits of CSP in Gansu compared with the scheme of wind and PV mix. Investing CSP will reduce the total capacity requirements of renewable energy and help accommodating other means of renewable energy, which are wind and PV, with a given renewable energy penetration level. Last, I would like to talk about the carbon capture power plants. 2 months ago, in September 22nd, President Xi gave a talk. He says that China aims to see carbon emissions peak before 2030 and achieve carbon neutrality before 2060. In recent years, China has built several carbon capture power plants, or CCPP. These pictures show 3 of them, which are located in Chongqing, Beijing, and Shanghai, respectively. This figure shows the energy flow in CCPP. If we compare the CCPP with the conventional generator, usually the emission from the conventional generator will be emitted directly. But in a CCPP, the generation circle is changed and the carbon capture part is installed as well. Because the carbon capture part is also consuming power as well, so the outputs of the generators will change. Particularly, the minimum output of the generator will be decreased, which could provide the extra capability to accommodate wind power. In this way, flexible operation of CCPP is very important. The operation region of the thermal power plants can be greatly expanded when it is equipped with a flexible carbon capture equipment. So, this will lead to three benefits: the deviation between the net output and the gross output, the breaking minimum output limits, and enable the wide range of output adjustments. We did a simulation on a real system. If we think about the installed capacity of CCPP, the curtailment of wind power will change due to the different capacity of CCPP. This figure shows three scenarios of this study, which shows the CCPP could help the wind power curtailment improvement. In this regard, the CO2 capture technology could be regarded to use the to-be curtailed wind power to do the capture. That means wind power could be supplied to capture system and enable full utilization of wind energy. This is very cost effective. So we propose to integrate the wind power operation with the CCPP, which can be shown in this figure. Although the renewable energy accommodation is significantly improved in China, several challenges need to be solved, and China is still on the road. There are several big projects related to renewable energy integration, supported by National Key Research and Development Program of China and National Science Foundation of China. We understand that lots of issues need to be further addressed. For instance, efficient operation and planning methods for the power systems, market design and practice for renewable energy integration, stability analysis of inverter-dominated power grids, accurate forecasting of renewable energy, regulation service from renewable energy itself, and grid-scale storage, and so on. Okay, let me summarize this presentation. We understand that the share of renewable energy in power system will continue to grow in China and around the world. In previous years, China has been facing big challenges because of the huge curtailment of renewables. China has been very successful in decreasing the curtailment ratio in recent years. The experience shows that it is important to take actions. Of course, we have a lot of work to do. Advanced models and methodologies should be developed to address the characteristics of high share of renewable power systems. Thanks for all your attention. I believe this conference will be a great academic event since the cross-fusion of power system and power electronics has become an important trend in the field of electrical engineering. Both Australia and China need a much smarter grid, which could be high penetration in both renewable energy and power electronics devices. Wish a great success of this conference, and may you all enjoy the conference. Welcome to Qinghua University in the near future. Thank you.
Okay, yeah, thank you very much for watching this pre-recorded keynote talk by Professor Changqing Kang from Tsinghua University in China. As he said at the beginning of his talk, because he's right now having the technical committee chair role in another conference exactly at the parallel and at the same time, so he couldn't, but he was very kind to pre-record this video and send it to us, and we had a very good overview about the high renewable energy penetration in China. So we just finished this talk now, and now we are continuing with our industry forum, which I do have all the panelists with us here, so we just I just change the screen and start with introducing our industry forum guests. So we have three industry experts with us: Neil Greet, Ruby Hurd, and Alan Reid. I just go very briefly through their bios, and then I'm just allowing that unmuting the screen, so unmuting, sorry, the microphones as well. So Neil is director of the Institute of Integrated Economics Research Australia and the owner of the consultancy Collaborative Outcomes. Neil was co-editor of the 2019 Engineers Australia and Australian Strategic Policy Institute report on designing for resilient energy systems, choices in future engineering, exactly the same topic of this industry forum today. Neil is an engineering executive and currently is the deputy chair of the Engineers Australia's College of Leadership and Management Board. Our second panelist is Ruby Hurd. Ruby is an ambitious entrepreneur and electrical engineer with global experience and a penchant for sustainability. She began her career with Arup, designing electrical and lighting systems for iconic buildings in Melbourne. In 2015, she transferred to Arup San Francisco office to apply her skills to renewable energy systems, complex solar arrays, and microgrids. After she completed a 6-month expedition for Engineers Without Borders in 2018 to support the United Nations High Commissioner for Refugees Energy team in Ethiopia, she founded Alinga Energy Consulting, a socially conscious engineering consultancy that provides specialist energy services to the commercial, government, and NGO sectors within Australia and internationally. Her company has a particular focus on areas with energy accessibility and affordability issues that prevent or limit the availability of reliable power. With Indigenous heritage originating from the Jaru people from Kimberley, Ruby is especially driven to find solutions for Indigenous communities. And our third panelist is Alan Reid, who is the Business Development Manager at Reposit Power, which is a world leader in innovative home energy monitoring and residential scale electrical storage management technologies. Founded in Canberra in 2014, the company has grown from 2 to 35 employees. Alan leads a team who is responsible for growing business revenues via identification of new business leads, negotiation and execution of commercial contracts, and delivery of a portfolio of large-scale energy projects across Australia. Alan holds, in addition to engineering degree, a Master of Business Administration MBA as well. So thanks very much all for joining us. And I guess you have to unmute yourself. Yeah, perfect. You're ready to go. Please go ahead.
All right. Well, thank you very much, Fahad. And it's great to be here to talk to this conference. And I appreciate the effort that conference organisers have gone through. And I do understand how difficult it is in this time to put together a conference and pull it together, you know, and people not being able to attend. It's a great effort, Fahad. Thank you very much.
Thanks very much. We were lucky to have all great supporters like you, great supporters as keynote speakers, tutorials, and more importantly, our all authors who have coming to us from almost 35 countries around the world. Please go ahead. Yes.
Yeah. So we've got till 4:30. So I'll be the time watcher now, and I'll make sure I hit that time for you, Fahad. If I might start by acknowledging the country, the first thing is I'm on the land of the Ngunnawal people, and I acknowledge the traditional landowners, the elders past and present. And I also acknowledge Ruby as an Indigenous person, and she's on as a panelist, and any other Indigenous people who may be part of the community that's watching us at the moment. So it's really important, and I hope you'll see that I don't just say that to start the session, but I think it's really important, and Ruby will come to some points. I've been to visit Budgebum, which is the World Heritage Aquaculture site just northwest of Warrnambool in Victoria. You know, and an extraordinary example that in a time before the pyramids, that a group of people were able to observe the natural environment and build a large-scale aquaculture system. And I think that idea of observing and being able to coexist is an important part of resilience as we go through. So look, this one's different to, I think, a lot of the other presentations. No slides, right? So you'll see our faces and we'll talk as panelists. So I'd ask all of you who really have engaged in heavy engineering graphs and diagrams, just to appreciate three people sitting and talking about ideas amongst ourselves and then giving you the opportunity to join the conversation. So I hope that gives you a bit of a feel. So I always do remember once not using slides in an American meeting, and one of the Americans remembered me for it and said, "Oh, you're the bloke who didn't use PowerPoint." So I don't know if it was a good thing or whether he thought I was a numpty, all right? So I can assure you I do know how to use PowerPoint, but I think this is just a different way. Let's embrace ideas and think about things. So specifically, Fahad did mention that the starting point is this report that we did release last year at Engineers Australia and the Australian Security Policy Institute on designing for resilient energy systems. And it's grown from an idea that I've been involved with, which is about energy security and the concept that we define energy security too tightly in saying it's only reliable and affordable energy. And as you know, Australia doesn't include emissions, whereas other nations would include emissions in that definition. Now, what I've observed, and I should confess, sorry, to this audience, I'm a civil engineer, all right? But I am doing a PhD in systems engineering at the moment on energy resiliency. So I come at this from a different background than perhaps a lot of the speakers have previously. Now, the concept is security, we need to put it in a different frame from what has been done traditionally. And the concept of energy security being a product of policy, regulation, and governance, and then you leave it alone and forget about it, I would suggest to you is the old world, the old systems, the old ways of thinking in an industrial age. Because what that does is that leads you to an endpoint of no change. What I would encourage everyone to think about is energy security is part of a dynamic ecosystem, and you must think about it in a broader way. You must think about change, adaptation, and mitigation. And here comes resilience, all right? Resilience is not reliability. I have seen technical electrical engineering papers interuse those two terms. They are not the same. Resilience is indeed about an ecosystem, a full ecosystem that includes people, community, political and social identity, technological systems, and dare I say, ethical and moral implications of decisions. And I get in trouble with some engineers, I will confess, because they say to me, well, that's not an engineer's role. Ethics and morals are somebody else's decisions to make. Someone else does that on our behalf before we take the design brief. I do not think that is right. I think when we look at the energy transition that we're embarked upon, and we have embarked upon it, that if we don't engage in the bigger systems in the ecosystem and consider resilience and security, then we are going to fail in the transition. And failure is not just a bit of disruption. Failure means we lose, people ultimately, and I don't want to sound too dramatic, but they lose their lives, they lose their livelihood, and the country will be in a complete mess, which is probably a little unfathomable for us at this point. So we did the report. One of the three things we wanted to emphasize was young engineers. If you take that concept of resilience and change and adaptation, then younger engineers have a huge role to play in it. And the idea is not older engineers lecturing to a younger set what must happen. It's about engaging with younger engineers. What are the ideas that they bring forward? because they will lead the change of the future. So this is leadership, and that's what the report was about. So we had Claire Painter from Maclistica. She did one chapter. Alan Reid, who we've got, did another chapter. Tara Lee MacArthur did one, and Jack Bryan. So of the authors, only one is Alan, but Ruby has been involved with energy resilience for a long time too. So they capture the spirit of that. So on that note, that's my statement to start things. So where we'll go from here is Alan and Ruby will give a statement in a similar way, then throw back to me, and I've got 3 questions I want to ask them. So we'll see how they go on their feet, and hopefully you'll enjoy the conversation, and then we'll give the rest of you a time to engage. So I think over to you, Alan.
Yeah, thanks very much, Neil. And I'd like to echo your comments as well. Big thanks to Farhad and all of the organisers of the event today. I think it's never easy organising an event such as this, particularly in these conditions. It's nice when you're able to look out and see faces of people you're talking to when you do a panel session like this, but I think this is the brave new world that we operate in, and this is our new normal. So it's not easy. So thank you very much for organising it and for having us talk today. I'd like to draw upon some of the themes that have already been discussed in the keynote speech, and then what Neil has said there today as well. I guess for where I come from, I'm a systems engineer myself, and I've always been around power electronics and involved in the national electricity grid. The context there is, as we all know, a context of a large industrialized society where big spinning generators, centralized generators burn coal or gas and then push that energy down through conductors to finally the endpoints where consumers then turn on their lights, their air conditioners, their computers, and all sorts of other things to consume that electricity. What we're seeing at the moment, and it draws upon a lot of the themes that were in our keynote speech there, particularly in Australia, and as we're seeing in China and all over other parts of the world, is this shifting attitude and culture towards renewable energy. We're seeing consumers of electricity changing their behaviours, changing their relationship with energy, and really trying to fight to regain a little bit more empowerment, a bit more control over their relationship with the energy they consume. It's no longer just about consuming energy blindly, turning on a light and having the light come on and that's it, you don't think about it. A lot of consumers these days, particularly around rising costs is one factor, and particularly around climate change and the factors in the environment that we're seeing from our traditional sources of generation. A lot of consumers now are starting to ask questions about how can I really empower myself and empower my community, empower the people around me to drive and really instill change in this generation mix. So it's no different here in Australia to what we saw in the keynote speech at the beginning there in China. We're seeing a vast uptake of renewable energies, and particularly decentralized rooftop PV generation. We actually hit a milestone in Australia in the end of 2018, where we had 2 million households with rooftop solar in Australia, which represents more than 20% of all residential dwellings in the country. So it's consumers who are off their own bat making the decision to invest in these technologies, invest in these to try and regain a little bit of that power back in the relationship with electricity. Now, this change in adaptation and adoption really of renewables, as I said, is driven by the changing attitude and sentiment towards renewables, but also the rising costs associated with electricity. So particularly here in Australia, and I'll give you the domestic context, the rise in the cost for electricity for consumers has been well and above the rise of anything else. CPI increases, wage increases, real wage increases. It's increased by a factor of 2 to 2.5% over the course of a decade. And that's really been part of the driver of the investment decisions made by consumers to get new technology, to get decentralized generation storage assets and put it on their roofs and their houses and where they live. So really what I'm interested in today and some of the topics I want to discuss is, we've got this sort of consumer-led drive to really uptake and push away from the old way of doing things in the electricity space into the new way of doing things with decentralized generation storage and new technologies that facilitate the aggregation and the leveraging of the power of those assets, such as the virtual power plant or you know, some of the concepts we saw in the keynote speech, such as the sort of cloud energy storage devices. And then what sort of things do we need from a regulatory and governance perspective to really drive good outcomes, provide certainty in investment decisions for those consumers and those big businesses who want to invest in renewables and further drive that change, so that we can really seek fantastic outcomes for everyone in the supply chain, not just the consumers, but also the people who own and operate the network, and everyone else from you know, commercial entities, businesses, the people who use and own electricity, and the people who have to own and operate the grid.
All right. Okay, Alan, thanks. Right. So we'll flip to Ruby now. So Ruby will give us a statement, and then we'll dive into the questions. Hope you're both ready. So Ruby, please.
Thanks, Neil. So as Neil mentioned, I'm a bit of a ring-in for today. I'm just stepping in for Claire, who couldn't make it. So I don't often get asked to talk about resilience in particular, but so I'll kind of talk about my experiences working in that space of resilient power systems. So my experience with resilient power systems is kind of on two ends of the spectrum, I guess. On the one end, I worked for a couple of years in San Francisco, and my focus there was on feasibility and design of microgrids. So mostly for the kind of commercial sector and the government. So microgrids have just seen this massive surge in popularity in the last few years, and so there's been a few different drivers for that. And as Alan mentioned, things like reduction in the cost of renewable energy, and but also these different change agents and disaster situations that we're going to talk about a little bit later in the conversation. But so traditionally, I think defence and universities were very good at jumping onto the microgrid chain pretty early. And part of that was because they had this huge driver of being able to see why they needed that resilient power system. So for universities, it's things like the prospect of losing research that just cannot be replaced, and defence is even more obvious. Yeah, so then the commercial sector started getting into this concept of microgrids, and I think that's because now we see how much of our businesses are totally dependent on having energy, and so many businesses can't operate without this continuous power, and then we've got data storage issues as well that are very sensitive. So the work I was doing was predominantly with Google and working on Google campuses in California. And so they had kind of an interesting take on their resilience, which I found interesting. So they had said to us, well, you know, if power did go down at our San Francisco campus, we could just move our operations to Germany or, you know, anywhere else. So they kind of had this interesting redundancy built into their workforce where they could just ship that work somewhere else if there was a problem. But having said that, they were still quite interested in looking at microgrids for their campuses. I also did work with airports and public transport. So I produced a paper on basically the opportunities for airports and public transportation with microgrids. So obviously they're hugely reliant on power, and they're also incredibly important for us in our modern society, especially in the case where there might be a mass power outage and it could be caused by some kind of disaster. It's so important to keep those transportation channels moving if possible. I did work for the city of San Francisco as well, which was kind of related to the aftermath of Superstorm Sandy. So that was at the end of 2012 and resulted in a power outage for over 8 million people. So it was considered the worst storm in US history in terms of power outages. So after that, the city of San Francisco was really interested in how they might replace diesel generators with solar and battery storage mini grids or microgrids, because basically the diesel generators just showed their true weakness after Superstorm Sandy. There was a lot of generators that they became flooded, so they didn't work. They were in basements, and also ones that didn't work because they hadn't been maintained properly throughout the year. So that really shone a light on just kind of how vulnerable those backup systems are, and they're supposed to be the backup. They're supposed to be something that you can rely on. And then now I do more work in power systems for remote communities. So that's kind of a different end of that spectrum. We don't have the grid. So these systems, the resilience and the redundancy of these is even more important. And so my focus there is really creating sustainable, maintainable, and resilient power systems for some of our vulnerable people in remote communities. Is that my time, Neil?
Yes, thank you. Thank you very much, Ruby. So yeah, that's great. As you've been talking, I've been reminded that resilience is one of those concepts that means many things to many people, right? And often as we say it, people will form in an idea that the resilience is for them, right? Or their component of their business, or they will want to put a money component to it. And what's really important, and as you've been saying, describing what you've done there, is the final one with working with remote Indigenous communities. And congratulations to you, because community is one of these words that's used in connection with resilience, but it is very hard to define. And I remember from my humanitarian work that people said, doctors save lives, right? Engineers save communities, right? But it's an abstract, because people can look at a doctor and a patient and say, oh, I get that, that's a relationship. So I wonder if you could just tease out for me how you think the community, what that relationship with community and resilience is, and if we can get a bit of better understanding of how the community works with disruptions and fits with resilient design. So you got that, Ruby?
Yeah, there's a few things in that. I'll try and tackle that. Yeah, so I mean, power systems are all about community. They're our consumers, our end users. It basically is just all about the community in whatever definition you want to give community. Obviously, there's a few different ways you can look at that. So when I think about that, I think about how power outages for many of us are just a bit of an inconvenience, a bit of a minor disruption. But now we're increasingly seeing that they can also be deadly. So I just looked up a random statistic, and it was a US statistic, but that's the first thing I found. So there was a little study done that said that non-accidental deaths increased by 25% as a result of power outage, so during and following a power outage, and accidental deaths up by 125%, which is just totally crazy. And so that's something that we're starting to see on the news more, is how blackouts are actually affecting people in a very disastrous way. So often blackouts are coinciding with these extreme temperatures, and we see vulnerable people lose their access to air conditioning, and it can be fatal. And so that's something that I think many communities are concerned about, that energy is so linked to our health and so linked to our livelihoods. It's just completely integral in our communities functioning and our communities living. And yeah, so the loss of it is just so significant. And in terms of the off-grid challenges, I guess they're similar, but they're just even more pronounced. So the things that I'm looking at are things like refrigeration. And I saw that a lot in my work in Ethiopia. These people couldn't keep vaccines. Their vaccines would go bad because they just didn't have stable electricity to keep refrigeration on. And that's something that we often take for granted. And if we experience a power outage, it just means, please, nobody open the fridge for the 8 hours that the power's off, or whatever, in the probably the worst circumstance. But yeah, for people in remote communities, it's so tied to everything. And air conditioning, again, is totally crucial for them. It's getting very hot in some of these remote Indigenous communities in particular.
Yeah, no, that's good. Well, you have been involved with resilience work, and you do know that some people are saying now that we're getting this divide with the remote parts of Australia. You know, they can't access what the cities have. Therefore, they're getting, you said it, hot, and they feel as no one's looking after them. and we wonder why we get this political and social divide in Australia. And these things are connected when you start to think about resilience. And it makes me think, Alan, you've been looking at the Canberra community specifically with Reposit Power, and you've had to grapple with challenging the conventional wisdom. And you've really had to grapple with regulation and governance and perhaps the old world of that as you've tried to bring in new ideas of community. So how do you actually, how did you actually go about it? And where did you sort of bring those concepts into your thinking?
Yeah, thanks, Neil. It's a really great question. And I think there's two key aspects of your question there that I'd like to draw upon and really reiterate what we've already spoken about. And the first one is, the conventional wisdom about regulation and governance in the electricity sector. And the second one there is the community sort of aspect here, because I think that's a really important key point that we need to draw out here, that everything we're doing here in advancing renewables, creating new technologies to help stabilize the grid, is to enhance the lives of a community. It's not for one person, it's not for one group of people, it's for the people as a whole. And it enhances the livelihoods of everyone around us. So the conventional wisdom part of the regulatory sphere and governance around the electricity sector has really, again, been a function of the fact that we've for 100 years done the same thing, and that's burn coal in those very large centralized power plants and then push it down conductors to the end connection point. Now those are big thermal machines, and they're very well-known entities. We know how they react. If we put a bit more fuel in, a bit more air in, they'll increase their power output. We've played with them for over 100 years now, over a decade, and we're very, very familiar with how they operate. So a lot of the regulatory mechanisms that we've got have been built around the certainty that comes with those generating units. We're certain that we do certain things and we'll get a certain behaviour out of them. I think part of the challenge that we're facing as an industry, shifting away from that sort of model to the new model where we've got decentralised generation and storage, particularly with the emergence of battery storage, lithium-ion storage. That's a very new technology. I mean, it's only about 30 years old. We've got a decade more experience with thermal generating machines than lithium-ion storage systems. So there's still a little bit of uncertainty, and we're still learning around them. The way they behave is based upon an algorithm. You tell it to do certain things under certain conditions. It's all software-based, and it behaves in certain ways. And it's a little bit more of an unknown entity, and we're really accelerating and coming to grips with what that means. But part of the challenge with the regulatory sphere is you might get a bit of an overreaction to that uncertainty. You might start to see a sandbox environment where we might just shift these assets off to the side to protect, what we know, what we're really comfortable with, and deal with these off to the side a little bit. But I think what we need to do, and again, drawing it back to that community aspect and really creating great outcomes for everyone in the technology stack of the electricity sector, is you have to treat all these generating technologies as equal and make sure that you're driving towards the same set of principles and outcomes with regulatory and governance. So you don't want to have one set of rules for one and one set of rules for the other. You just want to have the same underlying principles of reliability, safety, security of supply, low cost for consumers. And you really want to use those to guide you as to how to best create a framework that encompasses any generation technology and ensures those outcomes for the community.
Thank you very much, Alan. As you've been talking, and I deliberately put in there that term conventional wisdom, which actually comes from Professor John Galbraith, a famous United States economist who had to deal with the disruption of the Depression. And I don't think it's too much of an extension to think that we're on the cusp of another great economic wave of new thinking that breaks conventional wisdom. And I think the really important thing is that comes at the same time as everyone in this conference has been talking about the new technologies for the energy transition. So it's this concept of resilience, right? Resilience is not a stoic defense of the old systems, right, that keeps things going, but the adaptation to the new world and the change. Now, you've started to talk about, in fact, both times you've spoken, you sort of had change at the heart of what you're doing. But I think it is difficult. When I think a lot of people, when they say resilience, think of toughen up, keep doing things, and we'll get through this. I would like you to sort of, say how you think change has to be much more, a resilience is much more than the stoic behaviour. It's about change and adaptation and how you actually take people with you, because not everyone agrees with you, Alan. That's the world they want. I do, but not everyone else might. So how do you take people along that change journey?
Yeah, no, that's a really good question, Neil. And I think, the concept of change is not something that we can shy away from or be scared of. I think to really create those fantastic outcomes, as I said, for everyone in the technology stack, we have to ensure that their interests are looked after. We can't just, favour one particular group over others and leave others out in the cold. I think, a resilient electricity grid in the context of rising renewable energy systems has to be a grid that, as you pointed out earlier, is smart. It's adaptable, it's flexible, and it's much more resilient, for lack of a better word, than a traditional electricity system where you've got a high penetration of renewables. So, for instance, traditionally what we do with rising PV in Australia, particularly, is, there's a certain hosting capacity on the electricity network where if you get above a certain threshold of penetration of PV, then you have to have zero export limit everyone. So anyone from that point on who connects renewable energy generators to the network is not allowed to push any of that electricity onto the grid and not allowed to earn a return from it, because the grid has actually reached its maximum capacity of reverse power flow. Now, if we get smarter about this and we actually think about it, that's a bit of a crazy outcome. That's not a good investment signal for consumers. They want to be able to purchase these assets and get a return from them. So if we think about the increasing technological change that's coming here and the rise of the virtual power plant, and the idea that these assets can actually be controlled in smarter ways, it's not static. It's not something that's set at the time that they're installed and we just forget about it again. It's something that we can dynamically and in real time manage to the mutual benefit of everyone on the grid. Now, that all comes back to one thing I said there. I think, drawing upon your question of how do we actually bring people along the journey here, because not everyone agrees that renewables or a high penetration of renewables is the best thing for everyone. I think what we're seeing is, and again to draw on your point about economics, we're seeing an economic change here as well, where the thing that's really going to drive this, whether you believe in it or not, is the economics of the generation solution. So we're already seeing a point where new renewable energy plants are cheaper in terms of the levelized cost of electricity than large-scale coal-fired generation plants. So I think we need to have those outcomes in mind. We need to make sure that we have the outcomes for everyone in the stack in mind when we're building a framework around governance and regulation. And we need to make sure that supports clear investment signals for the marketplace to support and drive those outcomes.
All right, thank you, Alan. I was just thinking there, as you've spoken largely about electricity, is of course, and I won't take this too far down this track, but there's also liquid fuel security. There's also gas, and the ways we're treating those two is to keep relying on the old world. Liquid fuel, 90% of our liquid fuel is imported, and we're closing down our refineries, and it looks like soon we might only have one refinery left in Australia. It's that sort of trend where economics almost takes over the I'm going to say that word common sense, but it's a terrible word to use because it's actually not common. Is that the energy side of this is almost ignored to the where the economic extreme goes. So and it is, so then change becomes difficult, and communities look upon change differently. So I don't know Ruby, what's your spin on change and how you think about its relationship to resilience? And yeah, I'd be very interested in your thoughts. Thanks.
Yeah, I think Alan picked up the word that came to my mind, which was flexibility. Flexibility is the basis to me of a resilient power system, really. because change is the only thing that we know that is going to happen for certain. And I think we try to fight it instead of trying to just embrace that that's what's going to happen and trying to plan for it as best as we can. And our traditional grid is just the perfect example of where we've really missed the boat on flexibility. So we're struggling to respond now from going from this centralized system to a decentralized system, and from thermal generation to renewable energies. And I have this concern that we might just continue to go down these paths of not trying to be flexible enough. So I think the digital age is increasing flexibility for us just naturally. So that's something software upgrades and firmware upgrades. That's fantastic. So we can change things. We can respond pretty quickly when we can update things in that way. But I do wonder how people are thinking about renewable energy, and how I get this feeling that people think that we've already figured a lot of it out, that solar is going to continue to look the way that it does with PV and wind, and like these are our only options, and we've already found all of the options. And I think that people need to expand their minds a little bit and see, I do not think that solar PV is going to look the same, or the way that we use solar energy is going to look like the PV does today in 10 years or 20 years. And so I think we need to see our mistake from the past of thinking that we were always going to kind of have thermal generation the way that we do, and the grid was always going to be a centralized thing. And we need to try and look ahead and see, well, what could the next thing look like? We're not going to know what it is, but what might it look like? And so the digital age is bringing a lot of benefits to us in terms of flexibility, but we are still going to have these physical and technical challenges, and also regulatory challenges as well. So we've been way too slow to respond in the regulatory way to support these changes that technology is allowing us to do. So that's been a massive inhibitor. Our standards never keep up. You can barely get anything through regulations because they're just not keeping up with us. And there's also a big fear around new technologies as well. Like, the standards don't say that this is an option. So can it be an option? Can it work? Can solar and battery storage actually be a backup, or will only generators work? Because I feel like people are still stuck thinking it has to be a generator. That's the only thing we can really rely on. And it's just not really true anymore.
Yeah, just listening to that, Ruby, you've touched on a few things there. I'm interested where you say regulation and standards lag. Of course, regulations and standards will advantage the existing system, right? And one could argue there are perverse arrangements there that keep an old system going. Hence, that idea that resilience is stoicism, all right? And those two, that narrative comes together nicely. Something else you said about communication, and that the public might think that we've cracked this. I think engineers in this sort of conference, we can talk about the technology, but one of the things is we do have to communicate better with the public. We have to put faces up. We have to use words that mean something to them, and take them on the transitional journey. But the one big thing, I just want to come back to your original statement about your work in the States and in the recovery of US Superstorm Sandy. Our aim is always, after disasters, to build back better, right? So that's a concept of, it's a great concept, but if you think about what I just said about regulation and how the things that when you try to build back better, you're often constrained by the solutions of the past. And I just wonder how you might think about how future systems really do need to take into account vulnerability and change the way we design. So can you have a crack at that one for me?
Yes. So those big changes, they are, disasters, and obviously a lot of terrible things come out of them as well. But the benefit is that they expose some of the weaknesses in our systems, and they really force change. And they force us to think of better ideas and better systems and better ways of doing things. So Superstorm Sandy was definitely one of those catalysts which caused the US to reflect on the way that they were providing resilient power systems, and and they said, well, this isn't good enough. So that San Francisco project was really all based on, if this happens here on the West Coast, we don't want to make the same mistakes as the East Coast did. And so they were trying to get in front of it and say, well, we need to replace these diesel generators with something that we know is going to work a bit better. And so that was a fantastic project. And they looked at all the disaster relief buildings. We've identified them. I was working with ARIP at that time. We went out and we looked at the loads of those buildings and designed solar and storage systems that would cope with that emergency load in all of those important buildings in San Francisco. So yeah, climate change is especially a really big catalyst for resilient power systems. And so in my work, one of my big concerns and biggest challenges is the rising temperatures. And so how do we design systems that, particularly the energy storage, that can cope with these rising temperatures? And so I'm always asking manufacturers and suppliers, like, how hot can these batteries get? Like, because their solution is often to provide air conditioning, which is just, to me, adding in another system that has the potential to break down. And if my air conditioner goes out, then I lose my battery systems and I've lost my whole system. And so for me, that's not an acceptable solution, to say that you need another pretty vulnerable piece of equipment to ensure that I have this power system still up and running. So I really look for things that might thrive in a high temperature. I'm really interested in the kind of thermal batteries and things like that, just because that's working with what I've got. I've got an area that's extremely hot. I need something that embraces that and works with it, instead of something that's very vulnerable in that situation. So that's something that I'm really focused on at the moment. And during those high temperatures, that's the main time when we need these resilient energy systems, so to protect against some of the air conditioning problems I spoke about earlier. And then Superstorm Sandy really highlighted the benefit and the opportunity of microgrids as well. So I'll just quickly mention that during Superstorm Sandy, Princeton University, they have a 40 megawatt cogeneration microgrid, and they were able to keep over 4,000 apartments, 35 high-rise buildings, 3 shopping centres and 6 schools powered for almost 2 days. So that just shows you how beneficial microgrids can be.
I think there's a lot in there. Farhad, I'm just wondering, how will the questions go? Because I'd just like Alan to do a quick statement. We got 10 minutes here.
Yeah, I have already received one question in the chat box, which, if you want, I can read. It's exactly following that conversation which you immediately had about this, hurricanes or significant environmental impacts that things that impact the system. The question is that we are all talking about the resilience, which is considered to be incidents with quite low frequency but high impact. I suppose in academia, it's easy to study the transition to resilient grid. However, in industry, the story could be different. We need more resources in various aspects of the power and energy industry to make it happen. And the question is that I would like to hear some major challenges and obstacles we have in industry in the process of this transition. So transition to more resilient systems.
You know, Alan, I think that you might be well placed, because, you know, I wanted to get the statement to follow Ruby too, but that that idea of the barriers and stovepiping in industry and how that actually stops this response from happening. And I might just preface that by a little comment myself. Of course, we shouldn't call it the Bushfire Royal Commission. It was the Royal Commission into Natural Hazards and Emergency Management Arrangements. Didn't come up with any great, recommendations on energy. And in fact, I'm deeply worried that we haven't learned anything about energy resiliency from the fire disasters we were experiencing 1 year ago. But stovepiping in industry, Alan, I think, throw to you for that one.
Yeah, thanks, Neil, and thanks for the question. I think, you know, the response to, from an economic point of view, the response to, you know, things that move too fast is to tax them, and things that move too slow is to subsidise them. And I think I'll draw upon, you know, Ruby's point that she made earlier, that particularly and domestically, I'll draw upon my experience here in Australia. From an industry point of view, as working for an entity that really is heavily ingrained in this industry and working towards trying to proliferate these technologies amongst consumers and across the grid, I think what we've seen is there's this willingness, or at least this propensity, to try and subsidise these systems, to try and get investment happening as a price signal. We want consumers to invest in these systems. We'll put a subsidy on the table, and then all of a sudden we'll have a lot of PV systems and batteries in the field. The problem that we have at the moment is, to Ruby's point, that regulation lags that. Regulation is too slow, and when we're subsidising batteries, all of a sudden we find ourselves as, oh, great, we get all these technologies installed out there in the field, but now what do we do with them? How do we regulate them? How do we protect against negative externalities and bad outcomes that we otherwise hadn't considered? And I think what you see in the regulatory sphere is nothing, and then boom, all of a sudden there's kind of a big knee-jerk reaction when it becomes a material problem, where you've got enough of an installed capacity that it starts to have a material impact on the power flows across the grid. I think from an industry point of view, that's one of the biggest challenges that I think businesses face is, and again I spoke about it a little bit previously, and I'll come back to the point, is for a business who is on the cutting edge of this and is trying to work with consumers to get them to buy these assets and control them in a way that's best for the grid and best for them. You're in business to try and execute a business model. And, to execute a business model, you need to have some sort of investment certainty around the industry that you're operating in. If the investment certainty isn't there, if there's an uncertain market, then it's going to drive away investment. It's going to have the opposite impact. So you can subsidise at a consumer level the uptake of these systems, but unless you have a really sound and interlinked policy framework conversation that says, how do we draw upon what we're doing in the subsidising of the consumer space around providing investment certainty for businesses around actually working with consumers to solve these problems, you set up a bit of you kind of exacerbate the problem. You build a really large capacity in the field, and you take away the investment in certainty, or the risk is you take away the investment certainty for businesses who are well positioned and well placed to be able to go and get in there and solve those problems and really drive those solutions or those outcomes for the grid. So I think thinking about it from put on my hat as someone who works in the industry, as a business, a small business who works with consumers and works with policy and regulatory makers, I think that is the biggest risk that we face at the moment, is kind of this fracturing or this ill-disciplined or ill-considered approach, knee-jerk reaction approach to policy setting, because we've kind of thrown subsidies on the table. We've got consumers the market react to those subsidies, and then all of a sudden we're faced with this material problem that we didn't have before because we've accelerated it. I think that's one of the largest problems for industry. I think, just really quickly, I think the other problem that we face is that this is an incredibly complex marketplace. Energy is not easy to understand. I've been in energy for a long time and I'm still learning new things every day. For a consumer, the value proposition of these assets, it's a nightmare to try and wade through the complexity of this industry. So I think, again, where there's possibly a really big challenge for this industry moving forward is how do we boil it down from engineer speak to normal person speak, so that the community understands, and again, we're driving community outcomes here, the market understands what the benefits are of this product, how it operates, who it benefits, how it benefits them, and how does it actually make me better as well as my neighbour, and the person across the other side of the suburb there, or the person across the other side of Australia. That's what I think we've got to cut through, get through this engineering speak around electricity, and really drive home the consumer speak of why is this a good thing.
So Farhad, I think we might have one more question. I just want to, the start of your last questions came with, what do we do with low frequency, high intensity events, right? This is a really important thing. Emergency management people struggle with this concept of how are we going to resource these high disasters, catastrophic events that are coming. How do we build infrastructure that adequately addresses catastrophic events? Now, I think engineers aren't grappling with catastrophe, right? We want stable, stability systems is where good engineering is, right? But the danger's in the boundary conditions, all right? So that question, a lot more to it. So we'll just leave it there. And we've probably got one more question, I guess, And
Sure. Yeah. There is another question, and that is first thanking for the nice talk. What is the challenge to encourage renewable energy engagement in network operation from the perspective of policymaking and customer side? Very similar. Just a few minutes ago, Alan was talking about that. Yeah, but what do you think is the key challenge there? So we are accepting that there is a need for this policy and regulation update and these things, but why that uptake or change or things is slow?
So policy now, it's really interesting, this mix between market and policy and who leads who and all of that. And I personally am involved in trying to look at foresighting techniques that allow us to have a better understanding of how policy comes together, because there in the academic literature right now, policy and analysis has a strong connection, that the two drive each other. They're very powerfully connected. But foresighting and thinking about the future, which is quite powerful science and certainly not new science, doesn't actually connect with policy and analysis. And the reason for that is this real world economic need where the current systems, by and large, have their margins set and work within a system. So how do we actually get policy to move towards foresighting? And that I think is a real challenge. And I don't think the policymakers want to go there. So we have a reticence of people to do it. Therefore, we've got a technology roadmap, right? What does the technology roadmap tell us? It could tell us anything we want to read. Unless someone has the courage to put policy around that, then we have no idea where we're heading. So I could get quite animated personally about that one, but I'll leave it there. I don't know, Ruby, you didn't get a chance on the last question, whether you wanted to make some comments on policy.
Just quickly on what you said about the infrequent disaster events.
Oh, yeah.
So that's somewhere that I have done work in trying to show, well, you can get a diesel generator to respond in these events, but then the rest of the year, it basically does nothing. And it's the only value that the generator has is if these events happen. And so that's why we see solar and storage being a much better opportunity, because they can actually do work all year. And if the markets allow for you to get full benefits out of those systems, full economic benefits, then just like there's really no competition there with the diesel generator that just sits there gathering dust and needs maintenance. And then just on that, from the customer side, I would say in the remote community work that we do, the customer, the community engagement is just such an important part of it. Do you want renewable energy systems? Like what is it that you want in your community? That's the question that we're always asking. Me personally, nobody from my government, my local council, has ever asked me how much I care about the renewable energy penetration in our grid here. So yeah, I don't think that we do much community customer engagement like that, and we possibly should.
All right, we're on 4:30, Farhad, so I'll throw it back to you.
Fantastic. If you want, there is just one last minute question came, if you want, which is exactly very in line with the last few words of Ruby about the solar.
If you're happy to keep going, yep.
Oh yeah, well, we can go maximum of like 5-10 minutes, but then we have to immediately shut this meeting and then go and start with the new one. So it says, the comment is, thanks very much for the talk. As much as solar PV penetration is increasing, it's accompanied with varying output due to cloud events. My question is currently, how do we best mitigate the effect of these rapid ramp events, and what is the future of nowcasting, and can it enable an increase in PV hosting capacity?
Do you want to take that one, Alan?
Yeah, sure.
Your turn, I think, to speak. I think.
Yeah, absolutely. No, that's a great question, and I think you've hit upon one of the real challenges of dynamically managing, these generation assets on the grid, where you've got basically uncontrollable generation from PV. If a cloud rolls over, there's not much you can do about it. I think what the two things that you're able to do there to best manage the impacts on the grid are If you've got a smart device at that house that can not only look at the PV, but use the battery storage and other smart enabled loads, you can actually smooth out and balance behind the meter before it actually impacts the grid behind the meter, the generation and load dynamically. So the cloud rolls over and your PV drops right off. Your battery could step in and start exporting straight away to try and supplement that drop off, or you could cut load on the grid there behind the meter so that you don't have a massive step change in draw from the grid. So long as you've got smart enabled devices that work in an ecosystem together coherently, then you can manage those step changes. Now the other thing there that you can do. Sorry, I'm just reading the question again. We get these rates. So the other point I was going to make is around the nowcasting. So I think the better you can get at being able to forecast and predict when clouds come over, the better you're able to actually then use those controllable assets to control that generation. So at the moment, I think it's fair to say that we're still not great at this. Forecasting itself is a bit of a dark art. We can use centralized weather forecasting systems, which don't really give you really great confidence around scattered high moving clouds, where the PV is sort of going up and down, up and down. If you can get better forecasting systems that look at the sky and give you a really high fidelity, high accuracy idea of what sort of clouds are coming and how they're going to move over, then you can prepare those other assets to be able to actually mitigate those effects of those step changes. So you can balance loads and generation behind the meter, and if you can get better, more accurate forecasting, then you can be better prepared for what's coming.
All right.
Yeah, fantastic. Thank you. And luckily, we didn't get any more questions. Otherwise, I was going to keep you busy and not let you go. Yeah, thanks very much. Do you want to have a closing remark or?
Look, I think, Farhad, thanks again. For me, it's really important that we think outside our engineering technical expertise and what it means to the society and community that we serve. And that's not easy. And I think sometimes we engineers shy away from that and just develop solutions, right? And I think that's a flawed concept. So, Alan or Ruby, want a quick word?
I'd just like to again echo, thank you very much for having us today. It's been an absolute pleasure talking, some really great questions there. And I hope at least that these type of events and these types of forums can continue to really get people thinking about these problems and thinking about driving the solutions. I think that's really key here is, we do have this issue of resiliency with an ever-increasing penetration of renewables. We can't just bury our head in the sand. We've got to continue to have these forums, have these discussions in a collaborative way to really drive those great outcomes. So it's fantastic to see these sorts of forums continuing to allow us to have those conversations.
Yeah, thanks for having me today, guys. And I just wanted to point out something that I thought that was great that Alan just said in his last answer, which was about, reducing loads in response to some of these things that we can't control. We can control our loads. And I think that that's something that we don't often think about. We can have a little bit of compromise. I mean, I think lighting systems can be dimmed by like 30% and your eyes can't even perceive the difference. So imagine doing that over, whole buildings or whole communities and things like that. And same kind of deal with air conditioners. So maybe we need to think a little bit on the load side as well and how we can be more flexible to help with the resilient side of the energy systems as well. That's it.
Yeah, thank you. Thanks very much for all your great talks and interesting discussions which you had. Probably you can see in the comments as well, many people have liked it and they're positively thanking you. So thanks very much for joining us. And definitely it was a great honor for us to have you among us and supporting the conference by this interesting industry forum. People really from industry and from different aspects bringing that knowledge and sharing it with us. We just can hope that, generally this overall mindset and philosophy changes, that we must do things a bit slightly differently and make ourselves ready for changes and increase that speed of the uptake of those policies, changes, technologies, and the way we think. So thank you very much for attending this session. Sorry we went over time as well. And please feel free to join the rest of the sessions of the conference. And otherwise, have a very good time and good day. Thank you. So yeah, we are finishing this industry forum session now. So our presentation sessions are going to start in roughly 25 minutes, 24 minutes. So please, you have to click on those separate links for the presentation links and join the sessions. Thank you very much and see you in the presentation sessions shortly. Thanks.